There's still plenty of room at the bottom to generate piezoelectricity. Engineers at Rice University and their colleagues are showing the way. The work led by Rice materials scientists Pulickel, Ajayan and Hanyu and their colleagues at RIA's George R. Brown School of Engineering, the University of Southern California, the University of Houston, Wright-Patterson Air Force Base Research Laboratory and Pennsylvania State University appear. The discovery could aid in the development of ever smaller nanoelectromechanical systems, devices that could be used, for example, to power tiny actuators and implantable biosensors, and ultrasensitive temperature or pressure sensors. The researchers show the atomically thin system of a metallic domain surrounding semiconducting islands creates a mechanical response in the material's crystal lattice when subjected to an applied voltage. The presence of piezoelectricity in 2D materials often depends on the number of layers, but synthesizing the materials with a precise number of layers has been a formidable challenge, said Rice research scientist Anand Putharath, co-lead author of the paper. Our question was how to make a structure that is piezoelectric at multiple thickness levels, monolayer, bilayer, trilayer and even bulk, from even non-piezoelectric material, Putharath said. This allows one to engineer materials in 2D to create device architectures that could be unique in electronic applications. The junction is less than 10 nanometers thick and forms when tellurium gas is introduced while molybdenum metal forms a film on silicon dioxide in a chemical vapor depositio. This process creates islands of semiconducting molybdenum telluride phases in the sea of metallic phases. Applying voltage to the junction via the tip of a piezoresponse force microscope generates a mechanical response that also carefully measures the strength of piezoelectricity created at the junction. The difference between the lattice structures and electrical conductivity creates asymmetry at the phase boundary that is essentially independent of the thickness, Putharath said. That simplifies the preparation of 2D crystals for applications like miniaturized actuators. A heterostructure interface allows much more freedom for engineering materials properties than a bulk single compound, Zhu said. Although the asymmetry only exists at the nanoscale, it may significantly influence macroscopic electrical or optical phenomena, which are often dominated by the interface. Research scientist Xiang Zhang and graduate student Rui Xu of Rice and postdoctoral researcher Arvind Krishnamurthy of the co-authors are graduate student Jiawei Lai, research professor Robert Vaitai and lecturer Venkataraman Swaminathan of Rice. Priya Vashishta, a professor of chemical engineering and materials science, biomedical engineering, computer science and physics and astronomy at the University of Southern Cal. Zhu is an assistant professor of materials science and nanoengineering. He is also chair of RIA's Department of Materials Science and Nanoengineering. The Air Force Office of Scientific Research, FA 9550-18-1-0072, FA 9550-19 RICOR 050, and the National Science Foundation, 2,005,096, supported the research. Materials provided by Rice University. Original written by Mike Williams. Note: content may be edited for style and length. "2D boundaries could create electricity." Science Daily. ift.tt/qb20. Accessed August 16, 2022. Thanks for watching. Please subscribe my channel for more videos.